Hi, everybody. Ooh. Okay. So let me start by telling you a story, okay? So there's this guy, and he gets as a present this beautiful sword, this wonderful samurai sword, and he doesn't know what to do with it. So he asks around, and his friends tell him that there's a guy in Mongolia. If he goes there, this guy will tell him what to do with the sword. So he flies, he drives, he gets up there at the bottom of this mountain. He sees this house, he walks in, and he shows the guy the sword. And the guy takes the sword, and he takes a fruit from the bowl, and he throws it up in the air, and he cuts it perfectly in half. He's very impressed. So he says, "But that's nothing," the guy says. "You go up the mountain where my father lives. Ask him about how to use this sword." So the guy goes up the mountain to this expert father, and and he walks in. There's a hut there. He walks into the hut, shows the guy the sword. The guy shows him a fly up in the air, takes the sword and cuts the fly in half. He's really impressed now. He says, "But that's nothing. The real expert is my father up on top of the mountain." So he goes up to the top of the mountain, and there's a little hut, and he kind of walks in there, and as he's walking in, there's a little old man, and he shows him the sword, and the old man takes the sword, and he shows him a fly, and he goes, and the fly keeps on buzzing. He says, "What?" And he says, "Well, that fly won't have any children." So multi-core machines are this new sword that we have, okay? And all these experts that you're going to hear today, me and all the others, okay, we're still slicing, things at the bottom of the mountain. Nobody knows how to neuter the flies, okay? But we're going to try to teach you as much as we do know, okay? And that's what I'm going to try to do today. And I'm going to start by talking about maybe the most studied thing, the oldest thing that we know about coordinating, processes in a concurrent setting, and that is mutual exclusion. Okay, so that's what I'm going to talk about today. And let me see if I can turn this on. So I'm going to go through a sequence of lock constructions. And my hope is by doing that, I'll kind of illuminate the nature of modern locking processes, okay? And I'm going to start with simple things that many of you may have seen, and then I'll go to harder things and more complex things, and hopefully some stuff you haven't seen, okay? I'd like you to ask questions. I'm going to show code. I hope I'm going to go at the right pace given the time limitations. But please ask questions, because if you do ask questions, usually when you have a question, somebody else has the same question. So it's going to help all of us. So locking, mutual exclusion. I'm going to assume we all know you use this kind of an interface of, locking and unlocking. You wrap the pieces of code that you want to provide mutual exclusion for with this kind of a mechanism where we acquire the lock and then we release the lock. And we want to make some requirements on this kind of on these kinds of protocols, right? The first one is the property of mutual exclusion, right? This is a safety property. And what mutual exclusion says really that, essentially only one thread can be in the critical section at a time, okay? So only one guy can really hold the lock and execute that piece of code at the same time. And then we add to that a couple of additional properties. The first one, right, is freedom from deadlock. So if we only required safety, then it wouldn't be sufficient, right, because you could trivially implement it. So what we're asking here is that you provide progress, okay, a liveness property. So the way I define it is that if some thread calls the lock or the unlock method, essentially the only way they get stuck in either trying to get the critical section or trying to release the critical section is if the other threads are continuously succeeding. Okay? That's freedom from deadlock. And you could ask for a stronger property also, which would be freedom from starvation, which would mean that really every time that I call lock or unlock, I really succeed. Everything finishes. So I go into the critical section by calling lock, then I succeed in getting in there, and then I succeed in leaving the critical section. Okay? And this is independently of what the others are doing. Okay. So if this is our protocol for locking, okay, let's try to understand what it is that we want from locks. So the way I'd like to think about it is as follows. Imagine, let me see if this thing works. Yeah, it works. Can you see the pointer? Yeah, okay, great. So imagine, what is this? That's not me. No, I don't think so. I shut it down. Oh, it says it? On my computer? Oh, okay, okay. So that's not my problem, that's your problem. Okay, so let me continue while he fixes that. So imagine you have a concurrent program, okay? And in this concurrent program, imagine that 75% of the code is really unshared. I just wrote this parallel code, each thread does it on its own, okay? And the other 25% is the shared part, where I'm actually touching shared locations in memory, okay? So I have both of these programs are the same thing, 25% shared. And imagine that in one case, I use a coarse-grained lock to lock the complete 25%. Okay? And in the other case, I use this kind of fine-grained locking where I'm trying to get the granularity of locking to be as small as possible. The least number of lines actually captured in each lock. Okay? Oh, sorry. Yeah. So Amdahl's law, okay, tells me, right, that this formula for essentially the amount of speed up that I will get from this kind of code, which is essentially take the parallel fraction divided by n, and then add to that 1 minus p. 1 over that is the speed up, okay? What that really says, right, what that really says is that if I have 25% of the code shared and 75% of it unshared, okay, and I use a lock, okay, then what I'm getting here is essentially only a 2.9 speed up, okay? In fact, even if I had an infinite number of processors, if 25%, if a quarter of the code is sequential, I will only get a 4 times speed up, okay? So what I really need to do, okay, is to get this kind of fine-grained locking working, okay? So design locks that I can wrap small sections of code and do that with at the least overhead per lock acquisition. And that's what we're going to talk about today. Okay? Okay. Is there a way to fix this? Okay. Yeah, let's do it because it distracts me, and so if it distracts me, it distracts everybody. Sorry. Yes. Okay. 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 Okay, all right, so let's, yeah, okay, okay. All right, so okay, guys. So let's continue. All right. So okay. So the next question that I pose to you is, okay. So we've got this. We know now what we want to do with these locks. Okay. We want to essentially get, high performance kind of locking that is going to cost us very little. Okay. And the question is, what do you do if you're trying to get the lock and you don't succeed? That's the first categorization that I can do to locks. And there are two things that I could do. One is I could keep trying. That we call spin lock, a spin lock where I keep on trying to get the lock. Or I give up the processor, go to sleep, and have the operating system wake me up later. Okay? And today, I'm going to focus on the first part, on spin locks. Okay? The cases where I tried to grab the lock, I didn't succeed, so I try again. I don't go to sleep. I don't release the processor. So here's a basic spin lock schema, right? I have a bunch of threads. They run, they execute, they go through the critical section, they grab the lock, they go through the critical section, okay? And of course, a lock introduces sequential bottleneck. That is, the threads are actually going to go one after the other into this piece of code, okay? But there's another thing that a lock also introduces, right? And that is contention. Okay? Memory contention, interconnect contention. Okay? These are distinct phenomena. Okay? So, sequential bottleneck means no parallelism. Okay? They're doing it one after the other. That's the thing that hurts us in terms of Amdahl's law. But there's another phenomena, the contention phenomena, which is essentially means that I'm overloading the bus and I'm overloading, all the communication medium that leads me to the memory and back from it. And that will also introduce delays and cause the lock to be more expensive and affect us in terms of Amdahl's law. Okay? So I've got to solve both of these problems. So what we want to optimize, okay, in terms of the performance of these locks is the bus bandwidth used by spinning threads, the release acquire latency, and the latency to acquire when I have no other thread competing for the lock. Okay? So I'm going to start, okay, by reviewing some very simple locking algorithms. A basic primitive that we use to lock on a modern multiprocessor is essentially the test and set primitive. Okay? Here is the definition kind of in Java, if you look at it. So what I have here is essentially, a sequence of operations. Okay? I'm describing this as synchronized, but what I really want to just say is that this whole thing is done atomically, which is essentially I have, an operation that allows me, okay, to read the prior value and update it to a new value and do that atomically. That is to read and write from memory in one atomic operation. Okay? I'm swapping the old value and the new one. Okay? Now, what this means is that I can actually execute, a get and set operation like that in hardware with a value true, and that operation is what we call test and set. So if I do get and set true in Java, what happens underneath is a call to a procedure that actually does a test and set. And why is that working? Right? And both the swapping, where I use the hardware to swap to, the value of a register with a memory and memory with the register, or I set it to true. Both of these things are available in modern hardware, as well as stronger operations like compare and set and so on, which I'm sure you guys know. So a test and set lock, right? Very simple, okay? if the lock is free, the value is false. If the lock is taken, the value of this flag is true. Okay, I acquire the lock by calling test and set. Okay, and if I did a test and set and what I got is false, then I was the first guy because it was false before I set it to true, and everybody else is going to see it as true and not get into the critical section. Okay, so the winners see false, the losers see true, and I release the lock with a write. I don't need a synchronization operation for that because I'm the only thread. The one that's in the critical section is the only one that can release the lock. So you set it to false. How many people know this already, right? Everybody. Thank you very much. Okay. So now we go on, okay, to understand what's going on here. Well, what goes on here, right, is when I do this test and set, it invalidates the cache lines, right? And threads miss in the cache, they go to the bus, they overload the bus, and we start to get a deterioration in performance. Not because, right, of the sequential bottleneck, but because of the overhead of the attempts to acquire the lock. Okay? So if you think about it, the thread that wants to release the lock is competing for the bus with all the other threads that are continuously generating test and set requests on the bus. Okay? And therefore, we get bad performance. And so, many years ago, Larry Rudolph came up with the idea, this I think was in his PhD thesis, that what we do is a test and set. Okay? So what we're going to do is, we're going to lurk for a bit, okay? Wait until the lock looks free, and only then try to do the test and set. Okay? So I have a lurking stage where I'm just spinning, okay, for a bit, spinning essentially locally, on a local copy of the lock, and then the moment that I see that there was a change and somebody released the lock, then I try to go for it. Okay? This is called a test and set lock, right? And here's the code for test and set. So I'm using Java here to describe things. Let me just go over this code with you for a second. Okay? So what I do is, so this is in the lock procedure, right? I'm showing implementations of the lock procedure. So I have a loop, and in this loop, what I do is, okay, first I wait until the lock looks free. I do kind of a loop of reading, okay? And then, okay, after I've tried that for a while, I try to do, a get and set. Okay, this is the test and set part. And so what happens is, okay, right, that most of the time, when I'm spinning on a local cached copy. And because I'm spinning on a local cached copy, I'm not generating traffic on the bus. And because I'm not generating traffic on the bus, the lock works pretty well. Okay? So wait until the lock looks free, spin on a local cache copy, no use of the bus while you're waiting. Okay? But still, okay, when actually somebody releases the lock, then everybody generates, a request for the lock, and again I get this kind of storm of invalidations. Okay? So it's good, but it's not great because I still have all this competition, all these threads still trying to go for the same place in memory. Okay, how many of you knew that already? How many didn't? Okay? For those that didn't, questions? Please, just ask, because I'm going really fast. Usually I do this much slower. Okay, everybody's good? Okay, so, good. So, again, if everybody misses, the reads are satisfied sequentially, so everybody does a test and set and invalidates, and it takes a while after the lock has been acquired again until all this invalidation traffic by all these requests, okay, quiets down, okay? And this quiescence time is linear in the number of processes, okay, of processors, actually, of cores, okay? So this is, an improvement over test and set, but not that great an improvement. So here's how we're going to solve this problem. We're going to introduce a delay. Okay? So if the lock looks free, if I looked at my cached copy and I see, suddenly that it changed and the lock looks free, then instead of just pouncing on the lock, I'll wait a little bit. Okay? But how long should I wait? Okay? Well, if you think about it, right, if we all try to wait the same amount, maybe we're all looking, we all decide to delay, and then we all jump at the same time, right? That won't be very good. So what I'm going to try to do is I'm going to try to use this idea of delay to spread the processes out, to spread the threads out, so that each one of them arrives at a different time to the lock, okay? So this is the new idea. I'm going to do a kind of a back-off. I'm going to delay a little bit, but not delay everybody by the same amount, but rather delay everybody by a different amount. Okay? And if I could guess perfectly, and I could align them all with different delays, then they would just go into the lock perfectly, one after the other. Okay? So I'm going to try to guess what this perfect, organization order is. Okay? So the way we do this is with a process that we call exponential backoff, okay? So if I fail to get the lock, I wait a random duration before I retry, okay? And every time that I fail, I double the amount of time, okay, that I'm going to wait. But not that simple, okay? I'm doubling, but let me just show you what it is exactly that I'm going to double, okay? So here's what I do really, okay? Here's the code. So what I do is this. I introduce a minimum delay. That's my first guess, my initial guess for this lock. And then, okay, I do the usual thing of the test and set lock. I wait until the lock looks free, okay, and then if I manage to succeed and grab the lock, everything's good. Otherwise, I do a sleep of a random value within the delay range. So essentially, when I start out, I have some delay range. I try to throw the threads in some random positions within this delay area, okay, hoping that they spread evenly, okay? And if I actually didn't succeed, then for the next time, I'm going to double the range and again try to throw them into random slots, but this time in double the length of time, okay? And if that doesn't succeed, again, double that. But every time when I double the range, I am going to try to throw them evenly into this bigger range, okay? Now, of course, each thread is doing this using a different backoff. And still, people have proven, using a bit of stochastic analysis, that this algorithm actually delivers close to optimal performance. Okay? And so this is what we call, exponential backoff locks. Okay, questions? Yes. A question about sleeping. This is not, I'm sorry, this is not sleep of the operating system. This is, yes, I'm sorry. Yeah, let me repeat. So the question was, the sleep here, if this is the operating system, this will be very, very long. And so this sleep is not the operating system sleep. This is just our own code that just decides for a certain number of steps I'm not doing anything. A sequence of no-ops. Okay? Of course. So you're absolutely right. I don't have time to do an operating sleep here. Yeah. Yes. No. So delay is not shared between all threads. So each thread uses its own delay, okay? And still it'll come out okay. That's the beauty of the thing. They all do that separately. Okay? Yes. I mean, you could have them shared, but that's immaterial. The actual proof of this is even if they all use different delay values. Okay? Yes. So the only way that a thread will fail is if somebody succeeds. The problem that we have is that if too many of them, right? So here's the thing, right? How does a thread fail? It's because somebody else managed to win the test and set. So somebody will be in the critical section. So we know that we will always have progress, right? The problem that we have, right, is that the delays might be too big. And one guy succeeds and the next guy is backed off half an hour and there we are, sitting around doing nothing. And so this is where we have to use a stochastic argument to argue that actually when we look at the system as a this kind of dynamic process, then they will actually fall within very small intervals from one another. Yes, absolutely. Yes, yes. So every thread, every time, doubles the value if it saw that it failed. So it's kind of making a guess, a local guess, about what the global situation is, right? So it could be that one thread is guessing in a very small interval, and another thread is guessing in a very large interval. But it'll still come out okay. The value of the lock variable? No, so I'm not sure what the state is the lock? Ah, okay. Did you hear the question? The question is, how do you know if you're spinning on a local copy? How do you know that how do you see that there was a change to the global variable? Yeah, that has to do with the hardware that most multiprocessors have. They have a cache coherence protocol, okay? And you can assume that the cache coherence protocol will always guarantee, right, that everybody sees a consistent view of the memory. Yes. So every platform that is cache coherent, okay? And most of the multiprocessor machines that we build are a combination that allows that, okay? So there are different protocols. Typically, there's a protocol called MESI, and that's the protocol that most hardware platforms use. Yeah. Yes? Sorry? This algorithm is going to be deadlock-free, okay? But again, the guarantee here is a stochastic guarantee, okay? No. So the stochastic. Why don't you come afterwards and I will explain. Okay? This is a more elaborate question. Yes. Okay. So we need to choose the min delay and the max delay. You try. Okay? And in fact, that is part of the problem with this protocol. That you have to choose it so that you get good performance. Okay? And from one platform to the next, you have to choose a different value. Okay? It really depends on the application, on the processor, right? And in fact, there have been a couple of papers where people used machine learning to learn what the parameters are. Okay? But it's something that you have to choose. And here's what you get if you chose them correctly. You can see, this is on a 40-core machine. You can see that if test and set continuously, the latency rises. Test and set is slightly better. And a Backoff lock will kind of, pretty much stay flat throughout. Okay? This is the concurrency going up to 40, and this is latency without any kind of numbers, because I don't care what the numbers are. Okay? I want you to enjoy the shape of the curve. Well, this is up to 40 threads, so right here is 40 threads. This is the average latency. Average latency, yes. Yes, I agree. For real-time applications, the maximum delay will be interesting. Yes. Okay, good. So, yes. Typically, you can prove that it doesn't. Let me just say that again. Yes. I don't know. I'm going to guess, let me think for a second. No, I think this is, the test instead is going to have a catastrophic increase right after that, probably, yeah. Okay, so, right, easy to implement, beats the test and test set lock, you have to choose the parameters, it's not portable across platforms, so we got to do something better, okay? How long do I go before? At 11, before the break. Okay. Oh, that's good. So that's good. Okay. So, all right. So how are we going to avoid this? Okay. Well, what I said was that I was going to have these threads guess, where they are, right? And I'm going to do that by actually finding a way to kind of align them in time so that they have very short intervals between one and the next one, and then everything looks good, right? So how about instead that I keep a queue, okay, so that if one guy got the critical section, when he's done, he can just give it to a specific guy after him, and that guy will give it to the next one, like passing a baton, right? Like in a race, right? Okay? So if I could do that, okay, then maybe I can cut the delay times from one guy releasing the lock to the next guy getting it by a lot, okay? Because I won't be guessing anymore, okay? And the other thing that I can do, if I have one thread pass the critical section to the other thread, is that this won't involve a global process, okay? When we all saw that the critical section was released and we all jump on it, then we're all going and reading the same variable. Here, if I have one pass to the other, maybe I can avoid, the global communication and just have pairs of threads communicate. That'll cut down the amount of communication also. So let's try to achieve both of these things, okay? And the way we do that is with a lock, which is called a CLH lock, okay? The CLH lock is a first-come, first-serve lock, which means that it'll actually serve the threads in the order of the requests that they made to get the lock, okay? And it'll have a small constant time overhead per lock acquisition, okay? And here's how it works. So here's a thread, okay? And we have a tail variable, and we have a record, okay, for whoever's in the critical section, and it says here that it's false. Now, the thread that wants to come in will actually modify the tail, okay, the tail of the queue. And every time that you see that that this record is false, that means that the lock is free. When it's set to true, the lock is busy. So, purple wants the lock, okay? It creates a record for itself, okay? Puts true in there, and then does a swap between the value in tail and its own record, okay? So it points the tail to its record, and it gets what was in the tail. Okay, so again, the operation of swap, right, is register to memory swap like we saw before, right? register to memory swap of true is what we did to do a test and set. Now what we're going to do is we're going to do a swap where the purple guy swaps the value of what it has in its register, which is a pointer to this record, with the value in the tail, okay? And here we have it. So now purple knows about the guy before, okay? And the tail points to purple, okay? One swap. And now, for us, purple is now in the queue, waiting to go into the critical section. Comes red, does the same thing, creates a record, okay, and goes and performs the swap again. Swap, well, swap, there we go. And now red knows of what the tail pointed to before, which is the purple guy, right? And, you know, the tail is now pointing to this guy. Okay? Now, purple is in the critical section because he sees false here, so he can go into the critical section. Red can't go in because he sees true here. Okay? Right? So you can see that everyone is looking at the record of the guy before. And since purple had true here, red is spinning on it. He can't see, he doesn't go in the critical section. Right? Now, notice that what's happening here is this is actually purple's record. And this is red's record. Okay? So what we have here is an implicit linked list, right? They don't actually have a physical set of pointers here, but it really is the case that that you can have a chain of waiting like that. Okay? And in this chain, okay, you know, when the red guy is spinning, okay, and looking at this value true, the cache coherence protocol is actually going to copy the value of this location into the cache of the red guy. And so the red guy is going to be spinning on that value. He's not going to go continuously to memory, but actually just spin on the copy. Okay? Right? So that's what's really happening here. The efficiency of this lock is, so I do the swap, and then I start spinning, and immediately a copy is brought over to my cache, and from then on I spin on my cached copy. And so I'm not generating any kind of traffic.